Okay, so now let's do some examples of what this actually looks like when you try it in practice and why these integrals can be bad. Here's where we're at. We know that we have an expression ds squared is equal to dx squared plus dy squared if we're trying to rederive our formulas on the spot. Or we can consult our table and we can know that the length is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx, or length is equal to the integral from c to d of the square root of 1 plus g prime of y squared dy. Equipped with our formulas, we are ready to start solving problems. So here's a typical example. Find the length that I travel on the path given by y squared is equal to x to the third between the points 1, 1 and 4, 8. If I was going to draw a picture of that, you get this strange looking function that has two branches, an up branch and a down branch, and the branch that we're interested in is the one that starts at 1, 1 and runs up here to 4, 8. And the path that we want is this chunk right here. This is the L that we're looking for. Now, I can pick either formula at this point because I've got a function that's not solved for either x or y. For ease, given that most of us spend our lives working with functions of x, let's just write this as y is equal to x to the 3 halves. Okay, and the x values are going to go from 1 to 4. And now we're just going to write down the arc length integral. L is equal to the integral from 1 to 4 of the square root of 1 plus, okay, what is f prime of x? Because I have to put f prime of x right here. This slot is going to have f prime of x plugged in. So if f of x is equal to x to the 3 halves, then f prime of x is equal to 3 halves x to the 1 half. Okay, so let's continue. Basic mathematics is going to get us that this is the square root of 1 plus 9/4 of an x dx. And you can actually do this with a simple u substitution. If you let u equal 1 plus 9/4 x, then du is 4/9 dx. U of 1 is equal to 13/4, and u of 4 is equal to 10. And so after substitution, this integral becomes the integral from 13/4 to 10 of the square root of u times 4/9 du. Okay, so this integral is easy because it's just the integral of u to the 1 half. When you turn the crank on this one and the dust clears, what you're going to end up with is 8/27 10 root 10 minus 13/8 root 13. This is the kind of nasty integral that typically arises when we're doing arc length problems. And this one's not even bad because this one we could use a very simple u substitution to work on. What if we have a more complicated function? So here's a very straightforward example. I have a parabola and I want to figure out how far I travel between 0, 0 and 1, 1. The particular parabola that we're working on here looks like this because it's y squared is equal to x, and the path that we're considering is the path that goes from here to here, 0, 0 to 1, 1. Now, this is x as a function of y. So I'm going to think of this as a g of y problem. G of y is equal to y squared, and that means that g prime of y is equal to 2y. And now I can write down my arc length integral with limits of integration that are given by y values, because this is a dy integral. So the length of the path that I travel is given by the integral from 0 to 1 of the square root of 1 plus g prime of y squared dy. So that right there is the arc length integral. That's actually, in many cases, the hard part is getting the integral set up. And then you use numerics to analyze whatever's happening. For us, because we're learning this for the first time, we're going to carry through and try to get numerical answers. And unfortunately, this looks like an inverse trig substitution. So it's a tangent, obviously, because we've got a squared plus something squared. And what we'd really like to have happen here is that y is equal to half of a tangent of u, with the idea that we're going to use tangent squared u plus 1 is equal to secant squared u. Why the 1/2? Because the 1/2, when I square it, will cancel out that 4, and then I'll get the 1 plus tangent squared that I'm after. Dy is equal to half of secant squared u du. I might as well write this as u is equal to the arctangent of 2y, because I'm going to change the limits of integration. I don't want to change back. And if I do that, what I'm going to get is that u of 0 is equal to the arctangent of 0, which is 0, and that u of 1 is equal to the arctangent of 2. After substitution, we get the integral from 0 to the arctangent of 2 of the square root of 1 plus 4 times tangent squared u times 1/4 times dy, which was 1/2 secant squared u du. And all of this reduces to the integral from 0 to the arctangent of 2. This piece is going to become a secant. And then I'm going to have a 1/2 of a secant squared u du. And in real life, when you're stumbling around with an integral, not watching your math professor do it on a screen, if you stumble across a problem where you have a secant cubed to integrate, please consult a table. Don't grind this out by hand every time you do it. Secant cubed is one of those integrals that's a standard sort of integral, but you don't need to memorize it. Just go look it up. When you do, what you're going to find is that this evaluates to 1/2. The integral of secant cubed is one of those do it by parts and solve for the original integral. And you end up with half of secant u tangent u plus 1/2 of the natural log of the secant of u plus the tangent of u. And all of that is evaluated from 0 to the arctangent of 2. On application of the limits of integration, what we end up with is 1/4 of the secant of the arctangent of 2 plus 1/4 of the natural log of the secant of the arctangent of 2 plus the tangent of the arctangent of 2, which is just 2. The 0 terms all get killed. So this is the answer. And if you want, you can actually use the right triangle method to turn things like the secant of the arctangent of 2 into the square root of 5. Feel free. Or you can just leave it like this, because as a numerical expression, this is a correct answer. So what have we got? What are we taking away from this? We're taking away the fact that we have an arc length formula that looks like this. That if I've got a function of y, that I have an arc length formula that looks like this. And that I can derive an arc length function for a given function by writing down s of t is equal to the integral from a to t of ds, where ds is whatever arc length unit, whatever arc length chunk we need, based on whatever the input value of the function is. So if it was a function of x, we would use this ds. If it's a function of y, we use this ds. Don't get intimidated by the integrals in here, because these problems have been carefully selected so that they're either going to turn into u substitutions or they're going to turn into trig substitutions. There's really nothing else that can be done with these. So don't get scared away. Keep in mind that the arc length idea is one of the most powerful ideas in integral calculus, even if we have to use numerics to solve it. All right, so I will see you guys for surface area.